All right, let's get right into it. Today we are cracking open a scientific paper that, even though it's over 20 years old, really helped kick off a revolution in materials science. It came out of MIT's Lincoln Laboratory, and it gave us a pretty stunning answer to a really big question. And that question is this: what if we could actually capture and use the incredible amount of energy that we lose every single day as waste heat? I mean, just think about that for a second. You know, from the engine humming away in your car to these massive industrial power plants, a huge chunk of the energy they produce doesn't do any work at all. It just floats away as heat. It's honestly one of the biggest efficiency problems we have. Now, for decades, scientists have known about a potential solution: these special materials called thermoelectrics. The thing is, for the longest time, they just weren't very good. So, what exactly are they? Well, thermoelectric materials have this really cool property. If you heat up one side and keep the other side cool, they generate a voltage. They literally turn heat directly into electricity. And it can run it backwards, pump electricity through them, and one side gets hot while the other gets cold. We're talking solid-state refrigerators with zero moving parts. To figure out how good a material is at doing this, scientists use a single score. It's called the Thermoelectric Figure of Merit, or just ZT for short. For decades, the best materials were totally stuck with a ZT score of less than 1, which just wasn't efficient enough to be useful. Progress had pretty much flatlined. But then, a completely new idea started bubbling up from the world of theoretical physics. What if the answer wasn't finding some new bulk material, but in changing the very structure of the materials we already had, at the nanoscale? This is the theory of quantum confinement. The paper itself says it perfectly. Quantum dots represent the ultimate in reduced dimensionality. What they're getting at is, hey, what if we build a material from the smallest possible building blocks? Structures so tiny they're basically zero-dimensional points. Let's kind of walk through what that actually means. Okay, so in a normal 3D material, electrons can go wherever they want. But if you trap them in a super thin sheet, a 2D quantum well, now they can only move in 2 dimensions. Squeeze that down into a 1D quantum wire, and they can only move back and forth. And finally, if you trap them in a tiny little box, a 0D quantum dot, they're confined in all 3 dimensions. All their energy gets focused.
So why on earth does this matter? Well, in a regular material, both electricity carried by electrons and heat carried by vibrations in the material, they both flow pretty easily, and that's bad for efficiency. But in a quantum dot structure, those tiny interfaces act like a million little speed bumps for heat, slowing it way down. At the same time, the quantum effects create a kind of superhighway for the electrons. So less heat flow, better electron flow, you've got the recipe for a potentially huge boost to that ZT score.
But remember, that was all just theory. The team at Lincoln Lab, they set out to actually build this thing, to turn this wild idea into a real physical object that they could hold and measure. And this schematic shows their blueprint. It's brilliant. They use the technique called molecular beam epitaxy. You can just think of it like an atomic scale 3D printer, to lay down atoms one perfect layer at a time. By doing this, they designed what's known as a superlattice. And here's the unbelievable result. Now, this is not a drawing. It's an actual image from an electron microscope. Those little bumps you see are the quantum dots. And the craziest part? They didn't even have to place them one by one. The strain between the different atomic layers made them spontaneously self-assemble into these perfect little nano-islands. We're talking 90 billion of them per square centimeter. Just incredible. So, what was the secret sauce? Well, they used compounds of lead, tellurium, and selenium. The really clever part was the growth process they used, a method that basically encourages the atoms to form those perfect islands all on their own. And they didn't just do this once. They stacked over 600 of these repeating layers on top of each other to create their final material. So they built it. The theory was solid. The material was real. But the all-important question was still hanging in the air. Did it actually work? Let's look at the data. Okay, first, the baseline. This chart here shows the Z-score versus temperature. See that solid line? That represents the best performance anyone had ever managed to get out of the normal bulk version of this material. You can see it tops out at a ZT of just a bit over 0.4. That's the number to beat. And then they measured their brand new quantum dot material. And there are their data points. Just look at that. That is not a small improvement. It is a massive leap, completely blowing past the old record. The theory wasn't just right, it was spectacularly right. It all really comes down to this one number. At room temperature, that's about 300 Kelvin, they hit a ZT score of about zero point 0.9. This was, in every sense of the word, a quantum leap in performance.
Just to put that into perspective, here it is in a simple comparison. They took one of the best thermoelectric materials we knew of, and just by re-engineering it at the nanoscale, they basically doubled its efficiency. Doubled it.
So why are we sitting here talking about a paper from the year 2000? Because its impact went so far beyond just this one material. This was a true landmark achievement.
So how'd they do it? In their conclusion, the authors really boil it down to 3 key things. First, they very precisely added extra atoms to optimize the electrical properties. Second was that quantum confinement effect we talked about. And third, and this was huge, was the heat-blocking effect of having billions and billions of those tiny interfaces.
But the real takeaway is this. The experiment was a powerful proof of concept. It showed the entire world that by building materials from the atom up with what we call nanotechnology, you could unlock completely new, powerful properties that just don't exist in their normal bulk forms.
And this just blew the doors wide open for a whole new field of research. This work and all the science that followed is essential for developing technologies to recover waste heat from factories, create way more efficient cooling systems for our electronics, and even for powering deep space probes that go too far from the sun for solar panels to work.
It's a pretty powerful legacy for a single research paper, right? And it leaves us with a really fascinating question to think about. If this is what they were pulling off with nanotechnology way back in the year 2000, what kinds of problems will the nanomaterials being designed in labs today solve for us tomorrow?